Okay guys, welcome back to class. Let's go ahead and get started. I hope all of you guys had a very good recess week and were able to do something kind of fun. Okay, so we're going to continue talking now about the general linear model. So we'll start off with a brief recap about what we've talked about for the past couple of weeks, and then that's going to launch us into today's lecture, which is about comparing two groups. Now, hopefully today's lecture will be actually quite easy for you because we're talking about the t-test, and this is something that all of you guys would have learned in PL2131. So this is hopefully going to be a nice gentle way of easing you guys into thinking about comparing between groups, but thinking about this as a function of a general linear model. Okay, so just a brief recap. So for the past couple of weeks, guys, we've been talking about the linear regression and how a linear regression is a type of general linear model, or that it can be defined using this general linear model. Now, the general linear model, or the GLM, is something that hopefully all of you guys are familiar with even from secondary school, right? You guys were using this to calculate that line of best fit. So people kind of use different letters sometimes for it. You know, when I was growing up, it was mx plus b, but now we talk about b0 plus b1 x1. The whole point is that we can calculate a line that best describes this data as a function of the way in which the line slants, assuming it's a linear function, hence general linear model. So the slope of the line and where that line crosses the y-axis, right? And we're going to use this general linear model to help us predict outcomes. Now this leads us into the linear regression model. Okay, so what is a linear regression model? The linear regression is a way of regressing y on x. In other words, we're predicting the value of y. It's predicting the value of your exam score. We're trying to predict the value of your happiness score. We're trying to predict how likely are you to get a job after you graduate, right? It's anything that you want to predict. And as psychologists in training, you guys should be interested in trying to predict things in the future. What are the likely outcomes that you're going to see based on a set of predictors? And those predictors we're using to help us improve our prediction accuracy. Guys? So when we're doing a linear regression model, we're trying to predict what is the most likely outcome. And we're using a set of correlated predictors to help us improve our prediction accuracy. Because, of course, we could just look at the average. If we're trying to predict what is going to be your, let's just say, your overall happiness and well-being score 5 years from now, I could look at the overall happiness and well-being scores from the past 20 years, from whatever survey we're using to calculate this, and just make that as a prediction of your happiness score, which, I mean, it's okay. It's better than just coming up with a number randomly, right? But we can do better by looking at predictors that are correlated with your overall happiness, overall well-being score. And that's the whole idea of doing a linear regression. So we can use these predictors to help us improve our prediction accuracy, right? And the regression model is defined using that general linear model, that y is equal to b0 plus b1 x1. That's how we're defining it. And of course, if we have multiple predictors, we just simply need to add more terms for each of our predictors, because each predictor has a different relationship to the outcome. Okay, any questions so far? All good? So why are we learning the general linear model? Why are you guys learning about linear regression? Because it's really important. A lot of research in psychology and outside of psychology is based on the general linear model, and in fact uses a linear regression. It's using more complicated versions than just a simple linear regression. Oftentimes they have many, many predictors, and maybe they're using multiple things at once, but a lot of research, if you want to continue doing psychology, is using linear regression. And a lot of research is using, in fact, mediation and moderation. That's what a lot of research is about these days are, okay, we know something occurs. We know that when we give people alcohol, that they have poorer driving. We know that when people have more money, they report higher scores of well-being. We know that when people study more, they get higher grades. Okay, that's an effect. But what are the parameters of this effect? When are we most likely to see this effect, and under what conditions may we not see this effect? Those are moderation effects, right? Or why is there an effect? Why does studying more lead to better grades? Why does higher income lead to higher well-being scores? Those are mediation effects. And so we want to study mediation and moderation because, A, it's just interesting to know. And as psychologists, these are things that you guys are probably going to be interested in the future. And these are related to the linear regression because we're using that general linear model to help us understand and assess whether mediation is occurring, whether moderation is occurring. So mediation and moderation help us to understand the boundaries in which an effect might occur, the boundaries of a relationship. And it can help us to understand why is there a relationship between these two variables. Now, we use different ways of doing our regression model to help us assess for mediation and moderation. That's what we talked about before we all left for our break week. This is the idea of having hierarchical regression models where you get to choose the order to add variables, and then you can assess whether or not there is a significant increase in the proportion of variance explained when you add the variable of interest, right? So you have some amount of this variance is explained using your control variables. Once you add the variable of interest, whether that is your target variable or an interaction term, then you see whether this explains a significant increase in variance above and beyond that explained by your previously included variables. And so that's how we can use mediation and moderation within this idea of a general, of a linear regression model. Okay, any questions? Okay, so we'll start off with a woo clap. I want you guys to go here, and I want you guys to think about what is the difference between linear regression and a t-test. Okay, so let's look at some of these things you guys are saying. What's the difference between a linear regression and a t-test? We have t-test. It's hard when it keeps changing. So t-test is used to compare between two groups. Somewhere I saw that. Yeah, between two groups. We have comparison between the means. Linear regression predicts the change in the outcome, while a t-test is used to determine if there's a significant difference between the means group. Good. Let's see here. Yeah, linear regression is for relationship. T-test is for differences between groups. Yes, great. Linear regression aims for the value. Yeah, okay, so a lot of people are saying kind of similar things here. T-test requires categorical variables, while linear regression allows for continuous variables. That's correct. Linear regression predicts, t-test evaluates. Okay, so good. So we see lots of similar kinds of responses here. Okay. Okay, so yeah, so today we're going to talk about the t-test. And yes, you're right, that linear regression, we're trying to evaluate trying to predict a particular outcome. Now that is still, of course, true for t-tests as well. We're trying to predict, is there a significant difference between two groups? When we talk about linear regression, we're using a correlation to help us predict what the score of y will be based on a set of predictors. When we're talking about the t-test, we're evaluating whether there's a difference between the two means of these groups. So it sounds quite different, but in fact, they're a lot more similar than what you might think. And that's one of the reasons I asked you guys to think about this. Oftentimes, we're looking at the differences between two groups. Now, of course, we can go much more complex, and we can include 3, 4, 5, whatever groups. But we can do a lot of interesting research just by comparing two groups, an experimental group relative to some kind of control or baseline, right? Maybe we want to look at reaction time in groups who are stressed versus not stressed. Maybe we want to see whether there's a difference in the likelihood of a heart attack between people who have had a heart attack in some time in the past few years versus people who have not had a heart attack. Maybe we want to look at whether the exam scores will differ between people who declare that they like or are interested in statistics versus people who don't like or are disinterested in statistics. Or maybe we want to compare Singaporeans and non-Singaporeans on the number of holidays that they take overseas, right? So there's a lot of things that we can look at where we're comparing only two groups. And when we're doing a t-test, we are comparing two groups to see whether these means differ more than we expect by chance alone. Now, importantly, we are using a continuous dependent variable, just like what we do with linear regression. But as many of you guys noted, the predictor is categorical. When we're doing a linear regression, we can have categorical or continuous variables. When we're talking about a t-test, this is only for a single categorical variable that has, of course, only two levels. This is not new to you guys. You guys all know this from last semester. So we're comparing two levels of a single IV, and we can classify those two levels as maybe 0 and 1 to make it easier on ourselves. 0 being our control group and 1 being the experimental group. Okay, so the t-test tests whether two samples are likely to have come from the same underlying population. So we have our control group, and we're going to hypothesize that the control group comes from a population that has the same mean as our control group, right? And then we assess what is the likelihood that this experimental group, the group of interest, is coming from the same population. Okay. Now, again, we know that there's a lot of natural variation that exists in the world. So we don't expect, even if they come from the same underlying population, that the means of our two samples are going to be exactly the same, right? That doesn't have to be the case for them to still come from the same underlying population. And so we're going to calculate the probability that our experimental group is coming from the same underlying population as the control group, based on where it lies in this theoretical sampling distribution. So if it is somewhere in the hump or somewhere where a lot of samples are likely to occur, we would say, yeah, they're probably coming from the same underlying population. There's not any real difference between these two groups. If our experimental group falls somewhere in the tail of our sampling distribution, then we say it's unlikely to have come from the same population as our control group, right? There is probably a significant difference, meaning it's unlikely to have occurred by chance alone that we got this particular sample mean, because it's just so unlikely to occur by chance alone. It's just too rare within this population. Now, you guys know that there are two different types of t-tests that we can calculate based on the design. You've got a paired samples t-test and an independent paired samples t-test. Paired samples t-test, I'm just going to go through this quickly because this is all review from 2131. You guys know that the paired sample t-test calculates a difference score. So this is when you have a within subjects or a repeated measures type of design, like a pre-post, right? So you just calculate a difference score. So you say time 1 minus time 2, or time 2 minus time 1. It doesn't matter which way you calculate that, right? So you calculate a difference score for each one of your cells, and then you just calculate the likelihood of getting this particular difference score. So the paired samples t-tests test whether the average difference of two related samples is significantly different from 0, and it's calculated using that difference score over the standard deviation or the standard error. If we did an independent samples t-test, here we're going to calculate the difference between the two sample means. So we calculate the mean for sample 1, mean for sample 2, and then we calculate a difference score. So the independent samples t-test is going to look at where the difference between the two samples falls on a sampling distribution of differences between two samples. And again, we can calculate the t-test as the difference between mean 1 minus mean 2 over that standard error. All right, so this is everything that you guys have learned from 2131. Nothing new that I presented here. You guys have already knew that there are two different types of t-tests that you can conduct based on the type of design. A paired samples t-test is calculating the mean difference, right? It's you calculate difference score for each one of your like time 1, time 2, and then you calculate a difference score. So versus an independent sample is t-test is a difference between two means. Any questions so far? Okay, hopefully that was all familiar to you guys, because that's usually the way that we introduce t-tests and that we teach t-tests in 2131. And that's not at all wrong. But what I want to show you in today's lecture is how you can rethink the t-test as a type of general linear model. In fact, we can define the t-test through that general linear model that we've used for the linear regression. The whole idea is the same. I'm not changing what the t-test is used for. I'm not changing the calculations. I'm just going to today show you how the t-test can be defined using the general linear model that we've discussed in the past couple weeks. The reason I'm doing this is because next week we will start talking about an ANOVA. An ANOVA is going to be just a very small step from what we talk about today, because it's just, instead of 2 groups, it's just 3 groups. And we're going to think of it also as a general linear model. So to help you guys get there, we're going to go through the t-test because that's a bit simpler. Okay, so go back to your root clap. In linear regression with a categorical predictor, what does the B0 represent? Okay, so when we're doing a linear regression, like we've talked about for the past couple of weeks, B0, if it's a categorical, if it's a continuous predictor, we've talked about how B0 is where the line crosses the y-axis, right? When all predictors are set to 0, this is the predicted value of y, right? That's literally what it means when it crosses the y-axis, x is equal to 0. It's the same for categorical predictors. So B0 equals the average of the control group. Why? Because the control group is set to 0, and that's just what I'm going to show you now. Okay, so this is our linear regression model. Y hat is equal to B1x plus B0e, right? You guys have already learned that this means that the predicted value for y is equal to the value of y when x is equal to 0, right? So where it crosses the y-intercept, plus whatever the relationship is between x and y, right? If it's positive, negative, how steep it is, and then whatever value you set x to. Yes, this is this model that we've talked about in the past couple of weeks. Now, if x is continuous, this B1 is the slope. It's the change in y for every 1 unit increase in x, right? So it tells us how much of a change we should expect in our outcome as we increase our predictor, right? Or a decrease, right? If it's a negative relationship. Now the same is true when we use a categorical predictor. And we have done this already, but when we have a categorical predictor, the slope, or the YB1, is still the slope, right? It's still the slope of our model. But here, B0 is the value of y when x is equal to 0, which is literally the mean of our control group. When we have 2 groups, we're going to categorize them as 0 and 1. So when x is equal to 0, that's our control group. That means that this is our B0. So it's the same idea. When x is equal to 0, this is the value of y. Here, when it's categorical, when x is equal to 0, in other words, when x is the control, this is the value of y. And the slope becomes the difference between the group means. Okay, so I'm going to show this to you and break it down. But you guys recall that when we do a linear regression model, regardless of whether we're doing with categorical or continuous predictors, we will run a t-test. In fact, we do a t-test for every single predictor to assess whether the slope for that particular predictor is different from 0. That's the t-test literally that you guys are running. And that is what I'm trying to show you, is that the t-test is a type of general linear model. So you guys have been doing t-tests for a while. You've been thinking about t-tests, but I just want to show you how the t-test is actually just a GLM. You just haven't been shown to think about that. So when we do a t-test, be the slope over the standard error, that's literally mean 1 minus mean 2 over the standard error. Okay, so general linear models predict the score of y based on the relationship between y and a set of predictors. This is what we've talked about already. When evaluating a continuous predictor, the model we want to predict is the score of y. That's based on a set of predictors. When comparing two independent groups, we want to predict the score of y, which becomes the mean of our groups. So the model that we try to predict when we're dealing with categorical predictors is literally just the mean of each group. If I want to predict your exam score based on whether you like or dislike statistics, then I'm trying to use the average exam score for people who don't like statistics. And I'm going to say, if you don't like statistics, this is what I predict your score to be. If you like statistics, I will look at the average grade of people who say that they like statistics, and I'm going to say that's what I predict your score to be. And by using this predictor, it helps me to improve my prediction accuracy of what your exam score will be, above and beyond that what I would get if I was just to look at the average statistics exam score overall. Right? So it's the same idea as using a continuous predictor. I can predict your exam score based on the number of hours you study and improve my prediction accuracy of your exam score because I know that there's a relationship between hours studied and exam score. If there's a relationship between whether you like statistics or dislike statistics and the exam score, I can use that as my predictor and improve my prediction accuracy for what your exam score will be based on whether you like statistics or dislike statistics. Okay? So I'm doing exactly what we've done in the past. All I'm doing is I'm using a categorical predictor as opposed to a continuous predictor. But it follows the same pattern as what we talked about the past couple of weeks. Okay, so let's go through an example. All right, we're going to use the example of people who don't like statistics versus people who like statistics and try to predict their exam scores. All right, so this is some data. This is just imaginary data, but we've got 46 people who claim that they don't like statistics or are disinterested in statistics, and 54 who say, yes, I like statistics. I'm interested in statistics. Okay. Of the people who dislike or are disinterested in statistics, their average exam score is 52.11. For the people who say, yes, I like statistics, I am interested in statistics, their average score is 59.89. Okay? So this is the scatter plot here. And we are asking ourselves, what is the likelihood that these two samples come from the same underlying population? What is the likelihood that they are the same? Okay, so is there a significant difference between the two means of our groups? If we're using the no as our control group, we're asking, are the people who say that they like statistics or are interested in statistics different from a different population than people who say that they don't like statistics, at least when it comes to their exam scores? Now again, we don't expect that the means are going to be exactly the same if they come from the same underlying population. We know that there's natural variation that exists in the population of scores. So even though they are a little bit different, right, 52 versus 59, are these meaningfully different? Are these significantly different? That's what we want to know. Okay, now I can show you how we go through this. Y hat, this is the general linear model, so the predicted value for y is equal to b0 plus b1x. Now let's start off with our control group. No. That's equal to 0, right? We've got two groups. Our control group is 0. Our experimental group is 1. You guys choose which one you want your control group to be, but you should always put that one as your 0. We want to predict the value of exam scores if you have said, no, I don't like statistics. I am disinterested in statistics. So I'm trying to predict the average or your score, your score for no. This is the model I'm trying to predict. This is the score I'm trying to predict. Now, if we're talking about no, and no is equal to 0, that means x is equal to 0, right? Just like if I was looking at predicting your weight based on your height, and I might say, okay, height is equal to 173 centimeters, x is equal to 173. Here, because we're dealing with a categorical predictor, it's just binary, 0 or 1. So if we're trying to predict no, or the mean for group no, x just equals to 0. So we can cancel this whole thing out, and that shows us that B0 is literally equal to the mean of the group who answered no. So earlier, when I told you guys that B0 is equal to the mean of your control group, this is how we come to this conclusion. When x is equal to 0, all we're left with is B0, and B0 is equal to the mean of the control group. Now, earlier I also said that B1, the slope, is equal to the difference between the means. How did we get there? Okay, so let's go back. Now we're trying to predict the scores for group yes. Right? So this is the model we're trying to predict. Again, it's still being defined by the same way, B0 plus B1, x. But now x is equal to 1. Again, we only have two options, a 0 or 1. So x now is equal to 1. We know already B0 is equal to the mean of our control groups. We've already calculated that, so we can just fill that in right now. Therefore, if we rearrange the terms, B1 is equal to the mean of the group who says yes minus the mean of the group who says no. Hence, the slope of our model is equal to the difference between the means. Okay? So the slope here is equal to the difference between the two means, which is equal to 7.78. Therefore, we would predict that the mean for group yes is equal to 59.89. This matches exactly with the means that we have earlier. So all of this is simply to show you that when we do a t-test, the t-test can be defined using the general linear model. The t-test is equal to the general linear model is equal to the mean of your control group plus the difference between the two means. That's all it is. And then we can test whether the slope, that difference between the two means, again, if the slope is equal to the difference between the two means, and you guys earlier said a t-test is testing whether the difference between two means is significant, that's literally what we're doing. We can test whether the slope is significantly different from 0, which is literally saying, is the difference between the two means greater than we expect by chance alone? Is there a significant difference between the two means? So when we're doing a t-test, go back. A t-test is simply can be defined as a general linear model. Okay, questions? All right, any questions so far? Okay, so big picture. T-test. Is there a significant difference between two groups? That's what it's assessing. You guys already knew that. And you guys have learned that the t-test is equal to mean 1 minus mean 2 over the standard error of that difference. All I'm doing is showing you how that can be defined as the slope of a general linear model. So the t-test that you guys have calculated can be redefined as a slope. That's all I'm doing. Okay? So if we were to conduct a linear regression using this categorical predictor, like we have done for the past couple of weeks, we come down to the coefficients, and I don't know why this is not all the way down. I can't bring it down further, I don't think. No, unfortunately, I don't think I can. This is not a button. Oh wait. Ah, there it goes. Okay. So if we did a simple linear regression model, stop. Okay. Like we've done in the past, we would get our F model, or our F, right, that we've done before, and we could look down at the coefficients. We see that the slope B is equal to 7.78. That slope, again, is the difference between the two means, right? And then we can look at the t-test and see, yep, this is significantly different. So the difference between our two means is significantly different. So we're literally doing a t-test when we're doing a linear regression. And just like what you guys have learned in the past, the slope is the change in y for every 1 unit increase in x. But when we do this with a categorical predictor, it's the change in y relative to your reference category. It's relative to whatever it is that you've categorized as 0. So if no is our reference category, if no is the group that's 0, it's the change in the exam score and people who say that they like statistics relative to people who don't like statistics. Right? So the slope is always the change in y for every 1 unit increase in x. Here, we're comparing it to, when we go from 1 unit increase in x, we're just going from 0 to 1. So it's the change in y for people who like statistics relative to people who don't like statistics. If we did a t-test, if we just go back and rerun this as a standard t-test like you guys did last semester, then you would get the exact same values. T is equal to 2.170. Mean difference is 7.78. So all I'm showing you is that the slope for a regression model is literally the mean difference. It's the difference between those two samples. Okay? So the differences between means can be represented in terms of linear models, where the slope, B1, is the difference between that group's mean and the mean of your control group. Now you can imagine if we had more than two groups, we might need to have multiple coefficients, multiple terms for each one of our groups, and they're always going to be compared back to your reference group. So that's what we're going to talk about next week. But for now, we have just two groups. So we only need to have one term here, B1, X1, right? Okay, so the t-test can be defined using a general linear model, similar to how we've defined a regression line. When comparing two independent groups, the model we want to predict is the score of y based on the categorical group assignment. Now, model the score of y using the group means, and the slope is the change in y when you go from group 0, which is your control group, to group 1, which is your experimental group. So it is the difference between the two means. And the t-test is going to assess whether that slope differs significantly from 0. That's exactly like what we talked about for the past 2 weeks. Okay, any questions so far? Okay, let's go through briefly another example. I want to predict, does the method in which you take notes affect learning? So I'm going to look at taking notes from scratch versus taking notes while using the PowerPoint slides. Does this make any difference in how well you learn? I'm going to use the PowerPoint slides as my control group. Again, it doesn't really matter which one I chose, but I'm using this as my control group. And taking notes from scratch is my experimental group. Now, the null hypothesis is that there's no difference, of course. And if we're doing this as a t-test, we're just asking, is there a significant difference between these two means? Relative to the standard error, does the difference between our two means differ more than we expect by chance alone? Now we can go through again and show you how B0 and B1 is equal to the mean of your control group and the difference between the two means, but this is exactly like what we just did. The key I want to show you is that we can redefine our model here. So the predicted value is equal to mean of your control group plus the difference between the two means. Okay? So the slope, B1, is equal to 4.855. And this is the difference between the two means. And we're going to test whether this difference between the two means, whether the slope, B, differs significantly from 0. So that's the t-test. Here. B is equal to 4.855. Again, slope, difference between the two means, difference between experimental group and control group, and t-test. T is equal to 2.306. This is less than 0.05, so yes, they differ more than we expect by chance alone. So the slope is the change that you expect in the exam scores if you were to take notes from scratch relative to if you were to take notes using the PowerPoint slides. And again, we can redo this using a standard t-test and SPSS, and we would get the exact same results. Mean difference is equal to 4.855. This is significantly different. Okay, so let's bring this all back, because I know this can be quite confusing. So let's bring it all back. T-tests are used to compare whether the means of two groups are more different than we expect just based on chance alone. You guys already knew that, so that hasn't changed. Is there a difference between these two group means? In the GLM, this difference is represented as a slope. The slope is literally just the difference between the two means. The t-test will give you the exact same result if we do it as a linear regression model versus if you were to conduct it using a standard t-test from SPSS, because it's literally the same equation. It's literally the difference between the two means over the standard error. And that is what the t-test in the general linear model is doing as well. So all I'm showing you is that a t-test can be defined using the general linear model. Any questions? Now, I want to remind you guys, you don't even need to bring a calculator to the final exam. You're not going to calculate anything. What you do need to know is, what does this output mean? If you're to look at SPSS output and look at the slope, can you understand what this means? Do you understand that how this means that this is the difference in the predicted value of y in group experimental relative to group control? That's what the slope means, right? So if all of this is confusing, just come back to the fact that this is simply looking at differences between two groups, and the difference between two groups can be represented as the slope of your model, which is B. Okay, so that's it. Nice short lecture for today. T-tests are used to compare the means of two groups or two conditions. Now, traditional calculations involve calculating a difference score and comparing that difference to the sampling distribution of different scores. This is exactly what we're doing when we do a general linear model. We're just recalling the difference between the two groups. We're just redefining this and calling this now B for slope. But it's the same thing, right? In the general linear model, the y-intercept is the predicted value of y when the predictor is set to 0. Now, in the case of a categorical predictor, set to 0 means we're talking about the control group, because we've defined our two categories as group 0 and group 1. So when predictor is set to 0, we're saying that the mean that the B0 is equal to the mean of our control group. And B1 is equal to the difference between the two means. And then we conduct a t-test to determine if that slope is significantly different from 0. So this is exactly what we've done for the past couple of weeks. Right? We're calculating a general linear model. We calculate the slope of that general linear model, and then we test whether that slope is significantly different from 0. Okay, if you are still confused, do go back and read your textbook chapter. You can ask questions on the discussion forum. You can always email me for an individual consultation. Let's go through our quiz yourself. So go ahead and go to WooClap. Okay, so what does it mean if a t-test has a p-value of less than 0.05? Means that there is a very low probability that the experimental group comes from the same population as the control group. That's what it will always mean, right? If there is a p-value of less than 0.05, means the probability that the experimental group, or whatever group it is you're looking at, comes from the same population, the same underlying population as your control group. It means it falls into the tail of that sampling distribution. It's unlikely to have come from that same population. Therefore, it's more likely that it reflects a different population. Good. What does the t-test of a categorical variable represent? Yes, most people got this one correct. So the t-test represents the likelihood that the mean of that variable is different from the mean of that control group. Right? The t-test is literally just the difference between the two means over the standard error. Good. What does the slope of the constant represent? Okay, we've got a bit of a split here. The slope is the mean of the control group. So the constant, right, B0, is your control group. So remember that constant refers to the control group when we're talking about categorical predictors. If it's a continuous, the constant is simply the empty model. It's when all predictors are set to 0. So in this sense, it's when the predictor is set to 0. So it's a control group. What would the slope of a regression model look like if the experimental and the control group are equal? Yes, it would be flat. Okay, so the slope is the difference between the two means. If your experimental group and your control group are the same, then it's just going to have a flat slope, right? There's no slope. It's just flat line. Hence, t-test would be not significant, because that flat line is not significantly different from 0. Okay, what would happen if you code the control group as 1 and the experimental group as 0? Okay, yeah, most of you guys got this correct. It's not going to change anything. It's just that the results will be still significant. It just means the interpretation is the other direction. Instead of saying this is the change in the exam scores if you like statistics relative to if you don't like statistics, it will be this is the change in the exam scores if you don't like statistics relative to if you do like statistics. And so if it was a positive slope in the beginning, now it's going to be a negative slope, right? Or vice versa, depending on whichever one. So it doesn't mean that it's going to go from significant to not significant, or not significant to significant, or anything like that. It's going to be exactly the same outcome. It's just going to change the direction of the interpretation. Okay. Any questions from today? Yeah, good question. So let's go back. Here, this is what you're looking at, I think, here. So why is this slope positive, but the mean difference here is negative? It's just that they would have, in this case, they calculated it as the other way around. So no minus yes. here. It's the same outcome. It's just that in the t-test, they calculate it as no minus yes, whereas I was doing as yes minus no up here. But again, it doesn't change the outcome at all. It's just, it shows you that if it's a negative, it just means that they just flipped the way that they did the subtraction, basically. Yeah. Yeah, good question. Other questions? Okay, so that's it. Again, remember that when we're doing a t-test, all we're doing is comparing whether the means between groups differs significantly. And each group gets its own term. Now, one more thing. There is a data set on Canvas that you guys can try this on your own. So it's called it's a study about people looking at the effect of concussions on escape latency. Mice are given 0, 1, or 4 head concussions, and they looked at whether this influences the latency to escape from a maze. Now, they also looked at it whether mice are young or old. So you guys can go onto Canvas, find this data set, and try to run your own t-test using the linear regression and doing it as a t-test to see how these compare. I encourage you to first write out the linear regression model. Here's the data you need, but you can also have the data there. So write out the linear regression equation using young as the control group. Then conduct a linear regression with age as your predictor. And then conduct it using the standard t-test method that you guys have learned in the past. And just compare the results. I'll post the answer key onto Canvas so you can check your own work. Okay. Okay, so last thing, there is a survey. Some of you guys have done it. Some of you have not. So there's a survey on Canvas. It's the reflection survey for the ChatGPT assignment. I think it's important for you guys to recognize that these assignments are not just busy work. There was a reason for this. So I want you guys to go through the survey and reflect on what the assignment was for. What did you learn? How did you use the skills that you've learned in this class to accomplish this assignment? So if you haven't already, please go to the ChatGPT assessment reflection survey. It won't take you long. And finally, many of you guys have responded to the midterm survey. I'm going through that right now. I will post a short video about this onto Canvas, and I'll send an announcement. That's it. All right. Thanks very much, guys. If you have any questions, use the discussion forum.